Good day and welcome to Science and Nature. I am your host this evening. My name is Andrew Hebda. As our guest, we have quite an eminent geologist and researcher, Professor Dorothy Godfrey-Smith, who is going to fill us in on, over the next several shows, on some mysteries of time, mysteries of nature. And she's going to introduce herself, or introduce the first program by introducing us to the concept of radiocarbon dating and how this helps us understand what has happened in the past. Welcome to the show.
Thank you very much.
Now, the obvious very first question that comes to mind is, what is radiocarbon dating?
Well, I hope to spend the next 26 minutes telling you the answer to that question.
Very good.
I thought I'd start with radiocarbon dating as my topic for shedding light on the past, because it's the technique that is most applicable to the very recent past, the last several tens of thousands of years. Now, specifically, I thought I'd concentrate on this one because it's one that's applicable not only to the recent geology and glaciology, the dating of the ice ages and the changing climates, which is a very current topic, but also the archaeology of the New World and how the New World was peopled. And it's the one technique which, if given a choice, archaeologists choose to apply, supposing, of course, that is, they have adequate and proper correct samples for radiocarbon dating. But this is the technique to use in the New World. So this is my approach for the New World.
This is a very powerful tool, then.
It's excellent. It's wow.
Yes.
Now, for our first slide, we have the New World. For our second slide, for this New World, we have the, we have the geological timescale for the world. Now, starting down at the very bottom of the geological timescale, we see that the Earth is, in fact, 4.6 billion years old. And the time scale is not to actual scale. What it shows is that the first 4 billion years is scrunched up together near the bottom into the Precambrian. And then as we move up the table, the Mesozoic and the Cenozoic eras are defined by smaller and smaller divisions of time.
So these are in, the figures are in millions of years.
In millions of years. The Cambrian begins at 570 million years. And contrary to what my generation was taught on early morning cartoon television, you know, humans and dinosaurs did not exist at the same time, because humans actually evolved about 60 million years after dinosaurs were completely extinct.
We're very recent, yes.
We are recent. Anatomically modern humans are dated to about the last 100,000 years or less. Now, as we get closer and closer to the present time, we want to spend more and more time dwelling on the details, and this is also why radiocarbon dating is a great technique. Okay. How does it work? Okay. Now, on this slide here, we have an artist's rendition of the aurora borealis, the northern lights. And the northern lights occur through an interaction of cosmic radiation, especially charged particles, coming in from outside the Earth's atmosphere and interacting with the magnetosphere.
Yes.
And as a result, we get these beautiful northern lights. The same particles that interact with the atmosphere and create the aurora borealis also interact with some elements, specifically nitrogen, and from nitrogen, the interaction with cosmic radiation creates a radioactive isotope of carbon, carbon-14. Okay. Now, the normal stable isotope of carbon, which is present throughout the Earth, is carbon-12. Carbon-14 is radioactive, and therefore it decays over time.
Now, that's at a set constant rate of decay, then, is it, or?
A half-life. It has a half-life of 5,730 years. And what that means is that once produced, a quantity of radiocarbon will decrease so that there's only half of it remaining after that half-life. And if that's left alone, after another half-life, there'll be half again. Yes. So overall, a quarter. Now, all living materials, all living tissues, you, me, the plant behind me, we all have a certain quantity of radiocarbon, and that quantity is the same in all of us. It amounts to 13.5 disintegrations per minute per gram of dry living matter. So, you know, this is surprising to most people probably. We don't think of ourselves as radioactive. Well, in fact, we are. And therefore, by measuring the quantity of radioactivity in organic matter that has ceased to be alive, it's possible to determine how many half-lives back it had been alive. For example, if we were to take this plant behind me and pretend it's a large tree, and then allow it to be deposited in a geological deposit for several tens of thousands of years, okay? One thing that you will notice is that it gets very scrunched up. It gets squashed by the overburden.
Yes.
So that's one nice aspect that demonstrates to the observer that it's genuine, it's the real thing.
Yes.
Okay? It really is old, and this particular piece is very, very old. Now, if a sample remains in a geological deposit for, say, 7 half-lives, that amounts to 40,000 years. Okay?
That's determined by looking at the total amount of carbon and the amount and the percentage of that that's still carbon-14. Is that how it's done? Or?
Well, what we measure in the laboratory with radiocarbon dating is the activity of the organic sample.
Okay.
And we know the activity of modern samples, and we refer the activity of an old sample to the activity of a modern sample. And based on its very much reduced activity, we calculate how long it is since it has been alive, assuming that all matter has had the same activity while alive, both at present and in the past.
Right.
Okay?
Uniformitarianism.
Well, it is a form thereof. Actually, that's an assumption that needs corrections, but I don't think we'll go into those corrections today. So after 7 half-lives, there is less than 1% of radiocarbon left. Less than 1% of the activity that this wood had originally. Okay?
Okay.
So what that means is that even a very, very small contamination with modern material, active, will yield an erroneously younger age.
So contamination with hands,
So
any kind of material that
hands,
you're working with.
Carbon dioxide from the atmosphere absorbed into the material, various humic acids, carbon from groundwater, carbon from modern seawater, rootlets that go through old wood. I have seen actually a log, an ancient log, sticking out of a geological section with a little sapling growing out of it.
Yes.
Obviously, that piece of wood would not be radiocarbon datable because it had been contaminated with modern material.
Then, yes.
So essentially what this means is that by the time a sample is 40,000 years old, even a 1% contamination with modern material leads to a wrong age.
Right.
So this creates a natural boundary, upper limit for radiocarbon dating. In other words, we can say that once a sample reaches 40,000 years, the ages obtained using radiocarbon are not really secure. They can be used as a equal to or greater than age, but they're not really an equal than
You revert to things like potassium argon, or that's substantially longer than.
Okay. Now, the other point I'd like to make is that all organic materials are datable by using radiocarbon. So here is a very large piece of bone, okay? And right on the surface here, there is evidently a cut, okay? And this piece of bone was removed for radiocarbon dating and was submitted to a laboratory down in the U.S. which does commercial radiocarbon dating. What they did is they extracted the collagen, which is a protein of bone,
Yes.
and dated the collagen fraction, thereby ensuring that they dated material that really belonged to the bone, while the animal, in this case the mastodon from East Milford, this is his tooth,
Yes.
that the collagen was created while the mastodon was alive.
Right.
And the result indicated that this mastodon was greater than 37,000 years. Okay, so not a finite age, not a set age, but only a greater than age.
Yes.
Because of the very small quantity of radiocarbon in the sample. Okay, why don't we go to some of the other slides? Okay, well, this slide here shows simply the two types of living material which are radiocarbon datable, living organics of the animal kingdom and living organics of the plant kingdom, essentially. Okay. And what happens to them once they become deposited in a geological setting, when they are fossilized, if they have been fossilized within the last 40,000 years. These are bison from a bison kill site in the United States. They are also datable.
Right.
Okay. Okay. Pleistocene megafauna, if it's reasonably recent, the American mammoth, this is the imperial mammoth, which became extinct about 10,000 years ago. So the more recent specimens of this species are certainly radiocarbon datable, and various other forms of Pleistocene megafauna which are now unfortunately extinct. Saber-toothed tiger, giant ground sloth, mammoths and mastodons in the back, the dire wolf. These are all specimens that used to be alive in North America.
Up until roughly
up until the end of the glacial period, the last ice age. Okay. Now the other thing that is datable using radiocarbon dating is deposits which are relevant to human presence in North America, so archaeological deposits. This is an excavation pit at BFDA 1, which is an archaeological site, a Middle Archaic archaeological site in St. Croix, Nova Scotia, or what you would call St. Croix, I suppose, here. And if there is charcoal or any other form of organic material, burnt bone used, processed for food, seeds and twigs, which come from that period, the Middle Archaic period, that certainly would be datable using radiocarbon. Now, I just want to mention how radiocarbon came about, how it was invented. It was invented by an American scientist called Willard Libby in the 1940s, and he obtained a Nobel Prize for this invention in 1960. The slide we're looking at right now is one of the Sphinx, and that is because he proved his method using artifacts from the Egyptian civilization,
right.
From wood, from sarcophagi, papyrus, from Egyptian scrolls, and he demonstrated that the activity of these old objects is within error limits of the measurement,
yes.
very close or right on to that predicted based on the scientific principles.
Yes.
Okay. This one technique is probably the most powerful technique in the dating of the recent past, both in geology and in archaeology, and it really has changed the course of history, the course of our understanding of human history, of the recent climate changes. It created what's known as the radiocarbon revolution, because based on the absolute radiocarbon ages for archaeological sites dating to the Neolithic, the beginnings of agriculture, the beginnings of the great civilizations, very many archaeological interpretations dating from early in this century have been completely revised. And, you know, without it, we would really be up the creek and in the dark.
So things such as dendrochronology, for example, would help in some of the more contemporary material, but as you went further back, no longer had that continuity, that would no longer help.
Well, it's very interesting that you should say that, because dendrochronology is extremely important to radiocarbon dating because it provides a calibration of the radiocarbon dating method. Radiocarbon dating depends on the assumption that the production of radiocarbon in the upper atmosphere is constant and has been constant within the last 40,000 years.
And is that a reasonable assumption, or?
It's a reasonable but not entirely accurate, because of variations, natural variations in the Earth's magnetosphere, which shields the Earth and the atmosphere from cosmic radiation, and also because of variations in the solar production of cosmic radiation, there have actually been fluctuations, and there continue to be small fluctuations in the production of C14.
These are tied into normal sunspot activity as well? Like
That's one of them, for example. Yes, the sunspot activity on an 11-year cycle.
Yes.
There are variations on 200-year cycles, 400-year cycles, 2,000-year cycles, and then one very long-term one, which appears to be a very long sine wave that is evident all the way through to the limit of radiocarbon dating. So dendrochronology is terrific. Now the interesting thing is that because of these fluctuations in the production of radiocarbon in the atmosphere, the technique cannot be used for dating very recent objects.
I see.
So anything produced within the last couple of 100 years, you're up the creek. You can't apply radiocarbon dating
So
to it.
comfortably 1,000 years is a reasonable starting point? Or?
No, actually 200 to 300 years.
I see.
Beyond 300 years, you can obtain fairly secure radiocarbon ages, and then up to about 40, or using certain specialized technique as high as 45, 50,000 years. Okay, now I would like to go on to discuss a new method of radiocarbon dating. This is now known as AMS radiocarbon dating, or more simply AMS dating. AMS is an acronym for Accelerator Mass Spectrometry, and this approach allows the specialist to take very tiny samples of radiocarbon and date those, rather than needing several tens of grams or maybe half a kilogram of sample to date. All that is needed is really a few milligrams, 10 milligrams. So if we can go ahead with the slides to this one. Okay, here is an example of something that may be dated using AMS dating, which would not have been datable using conventional technique. It is a calcium carbonate cast, a 4am cast.
Yes.
From an ocean sediment. Okay?
Now, for a very, very small, you're looking at something that's perhaps half a millimeter in size?
About that size.
Yes.
Right. So by collecting a few of these, enough to make 10 milligrams or you know, conservatively 100 milligrams of sample.
So for those that aren't familiar, 100 milligrams would be a tenth of a gram. Would that be correct?
Yes, that's
okay.
right. Thank you. So very, very tiny quantities can be submitted and dated securely.
Yes.
Okay, something that would have been impossible 10 years ago.
Yes.
And again, this has really overturned many interpretations, because based on AMS dating, we can now date, for example, the organic residues on spear points, on projectile points, which were used to butcher animals that early people had used for food. And that approach simply entails the washing off of this organic residue and submitting this very, very tiny concentrate, which is all but invisible on the tool itself, for dating.
So those could be proteins or virtually anything.
Proteins or fats.
Yes.
Okay. What it also means is that samples, like tiny, tiny fragments, vertebrae, individual vertebrae of rodents, or little foot bones of rodents from sites, geological or archaeological sites, can be dated individually and dated securely. Again, an impossibility prior to this.
Yes.
Now this slide, I put this one in because here is another useful approach to AMS dating, and that is, what this slide shows is a volcanic eruption with tephra flying in the air. That tephra will be carried by the wind and deposited at some distance in lakes and on the earth, and then later perhaps washed into lakes probably within one season.
Now, tephra being a light gas-filled material, then, is it, or is it?
Tephra is a very light, glassy, sort of very powdered, fine rock material that is ejected from a volcano.
Not like obsidian, similar to obsidian, but much lighter then.
Much lighter because
Yes.
it's smaller, because these are small, bubbly sort of pieces.
Yes.
The tephra flies around, but as it falls, it acts like a scouring agent for the air, and so it drags everything else down along with it.
Oh, yes.
So what else is flying around in the air that's organic? Pollen,
Yes.
right? So we have the possibility to date directly individual pollen grains. And by dating these pollen grains, okay, while they're floating in the air, you know that they must have been ejected into the air that season.
Yes.
So we can actually date things like tephra deposits directly by dating the pollen grains, just a few pollen grains, maybe 10 pollen grains of one single species that is bound into the tephra deposit that has been scoured down with it.
To give you a very precise date for a particular sediment. Yes.
It's tremendous.
Yes.
Now, I put that one in. We can turn back to archaeology again. Using conventional radiocarbon dating, this carving made on a bone would not have been dated. Nobody would dare to date it using radiocarbon because it would destroy the object completely and
Yes.
therefore destroy a valuable
Artifact.
part of our cultural resource, our cultural heritage. And I'm speaking of us as members of the global village rather than us as just members of Nova Scotia, because this particular object certainly wasn't created in Nova Scotia. Using AMS, a very small piece can be drilled out of the object on the side where it's not visible without destroying its cultural value, and allow the carving, the bone at least, of the carving to be dated directly.
These dating techniques are destructive, though. The samples themselves, as small as they are then destroyed. Is that correct? Or do you
They
still
are
have the residue
destroyed,
left afterwards?
yes, yes.
But in this case, it's very insignificant as compared to the bulk of the object. Yes.
It's a hole that would be about the size of one of the smaller nails that you might use in working around the house.
Okay.
Well, I'd like to go back to ask one question, and that is a question of when did humans actually arrive in North America? Okay, this is a very good question to use radiocarbon dating for, and it's a very relevant question because there are tremendous misconceptions about it, and depending on what literature you read, you know, some optimistic estimates might go back as far as 20, 30, 50,000 years I've
Yes.
seen in the literature. In general, there are no archaeological sites which are securely dated which have the association of radiocarbon date with clear humanly created artifacts within an age greater than about 12,500 years.
Okay.
The reason for this is that prior to this, North America was covered with ice age, with ice. Okay, certainly the northern part of North America, that is all of Canada. During the last ice age, and what we see on the screen here is North America with the continental shelves outlined in a sort of a light cyan blue. Can we have a slide, please?
So this particular case, then, essentially you had both a covering of the material with covering of the ground with ice, as well as compression and a variety of other things like that. Can we go to the slide? Is that possible?
Yeah. So you will see that now we can for the purposes here of our discussion, this indicates that most of North America, including a bridge between North America, Alaska,
Yes.
and Siberia, was uncovered because the ice that is presently in the ocean was actually bound up as ice and
Yes.
was sitting on land. And during that time, humans came into North America, into what's known as Beringia. One very interesting artifact that was discovered in Beringia about a decade or a couple of decades ago is a lovely long flesher, very clearly worked by man or woman. And most of this piece was submitted for radiocarbon dating.
Yes.
And an age of greater than 27,000 years was obtained for it.
Very significant.
This
then,
was
yes.
very important because it indicated that people reached North America by 27,000 years. This was an age obtained on bone apatite, which is one of the components of bone.
Right.
And it turns out it's a component which is not stable in situ. In other words, it's an open system. It exchanges its carbon with its environment.
Yes.
So using AMS dating, this flesher, of which only a little tiny portion remained by the late 80s, was redated, and it was found to have been created within the last few thousand years.
Oh, so it's much more contemporary than
So
yes.
it's completely contemporary. There are many other archaeological sites in North America that predated. And at this point, it seems that there are no archaeological sites in North America which predate the Clovis period, except for for one site in Beringia, which is only a few hundred years older.
So in the last half moment or so, what do you see the future? You see the future actually as being quite bright with respect to pushing back some of these dates or clarifying dates, or?
My own feeling is that considering the enormous wealth of archaeological sites dating well back in the old world, which are not hard to find at all, and the tremendous difficulty in finding anything that is securely datable to pre-13,000 years before present, I think that's highly unlikely.
I see. So what I'd like to do is thank you very much for coming and sharing us this the fascinating techniques, or a series of techniques. And perhaps what we'd like to do is, if we could, we'd like to have you come back and perhaps tell us a little bit more about our history or prehistory, perhaps going a bit further back beyond the contemporary dates we've talked about. So if anybody has any questions on radiocarbon dating, you're certainly welcome to to come and visit Dr. Godfrey Smith at the Department of Earth Sciences at Dalhousie University.
Thank you very much, Andrew.